All right, so 7.6, we've been working with polynomial functions, things that are bigger than powers of 2, different things like that. And the next lesson, 7.6, we're going to be learning how to solve polynomial functions. So we're going to need some skills that we've used before. One of them is factoring using the X method or difference of squares or other techniques. So we're going to review some of those and then talk about some new ones. So first, let's look at this example over on the side, 2x squared minus 7x minus 15. And I'm going to review this using the X method. So remember, I'm going to draw that X. The top number is when I take this value and multiply it by the last value. So 2 times negative 15 is negative 30. And the middle number, negative 7, is what goes on the bottom. And what I'm looking for is what numbers multiply to negative 30 but add up to negative 7. So maybe I look at, well, 1 and 30. 1 and 30, there's no way that those can add up to 7, so that doesn't work. Maybe 2 and 15. Right now I'm just listing things that multiply to 30. 2 and 15, well, I could get 13 if I subtracted them. I don't know, I can't get 7. How about 3 and 10? Ooh, bingo, I think that's going to work. If I made this a negative 10 and a positive 3, then negative 10 times 3 is negative 30. Negative 10 plus 3 is negative 7. Okay, and then remember, I'm using these values to split up this middle number here. So I'd have 2x squared minus 10x plus 3x minus 15. Okay, so notice the middle numbers, if I did negative 10x plus 3x, it would still be the same as this value that I had here of negative 7. And then when we get to this point, when we rewrote it, now the whole point of that was so that I could factor by grouping. So I'm looking at these first two, and I know what they have in common is a 2x. When I take out a 2x times x gets me back to this 2x squared. And 2x times 5, or negative 5, gets me back to this negative 10. And then I'm going to repeat. Okay, how about these two? Well, what goes into those is a positive 3. And then I should see my parentheses start to match up. And then I have one last step. Well, what's in common? They both have this x minus 5. And x minus 5 is getting times by 2x. And it's also getting times by positive 3. So this would be that factored form. Okay, and that's review of some things that you did last year or potentially maybe even earlier this year with factoring. Okay, number 2. Another technique is kind of what we did at the end of that last one, which is just take out the GCF, greatest common factor. What is the biggest thing in common with all the terms that I have? So I'm looking at 25 and 15. 5 is the biggest number that could be divided by or divided into both those. I could also take an a squared from each and a b to the 5th from each. So that's my GCF. That's the greatest common factor. But remember, when we rewrite this, we want to say, well, what would I multiply? I want to have something at the end that's equal to what I started with. So what would I multiply 5 by to get to 25? Well, that's 5. A squared times a gets me a to the 3rd. And b to the 5th, well, I already have that, so I don't need any more b's. Plus 5 times 3, that gets me to 15. A squared, well, I already have that taken care of because it's right here. And then I would need another b. So this would be a factored. So that's a little different, but that's factoring out what's the largest thing in common with both. Okay, and then number 3 here, we have another example, but it's one of those special cases. Okay, so I'm going to actually type this up here. It says special cases. And this one is difference of squares. Okay, difference of squares, meaning I have something to the second power minus something else. And a and b could be any numbers, right? A just means something to the second. B is some other thing to the second power. And when I have something in this form, I can factor it to be a plus b and a minus b. That's always the factored form of difference of squares. So the trick is now for these, I got to figure out, well, what is being squared? So instead of a, I can obviously see I have x squared minus, well, 81. How could I write that as something being squared? Well, I know that's 9 to the second power. 9 times 9 is 81. So why I'm writing it that way is just so you can see, instead of wherever I see a, I'm not going to put a, I'm going to use x because x is what's being squared this time instead of a. Anywhere I see b, instead of using b, I'm going to put 9 because 9 is that value. So this factored form would be x plus 9 and times x minus 9. And some of you might remember that, so maybe I'm talking too much, but that's difference of squares. That's how we would factor that. Okay, so let's keep moving. Here's some other things that are new. These formulas, you may have to pause the video if we want to, but these formulas, difference of two squares, that's what I just wrote. Now we have sum, which is adding between two things that are being cubed or raised to the third power, and difference of two cubes. Okay, but up at the top it says when factoring polynomials, take out the, you guessed it, GCF first, then factor the result. So technically this doesn't really matter. You don't have to take out the greatest common factor first, but pretty often it makes it a little bit easier if you take out what's in common first and then simplify what's left. But it's not technically, you don't have to do it that way. All right, so there's our formulas for those difference of cubes and sum of cubes. And then we'll talk about how to use those. All right, so here we go. I'm going to start with number 4, x to the third plus 125. The first thing I'm seeing is that is a sum because we're adding. And I know this first piece is being cubed, so I'm going to try to rewrite 125 as something that's getting raised to the third power. So that something is 5. 5 to the third power is equivalent to 125. So if I go back a slide here and I look back at this formula, a to the third plus b to the third. Well, instead of a, anywhere I see a in this formula, I'm going to replace it with x. And instead of b, that second thing being cubed was 5. So that's how I'm going to fill into that formula. Okay, so if I look at that, I would have this is equal to x plus 5 times x squared minus 5x plus 25. So I was filling into the formula, which was a plus b times a squared minus ab plus b squared. And I just said, like I said before, instead of using using a, I'm replacing with x, because that's the value that's being raised to the third power. Instead of b, I'm replacing with 5. So that's how I got to that point. All right, let's look at this one. I always try to do this first step of saying, what is getting raised to the third power? What is being cubed? So that I can say, well, what is a and what is b? So in this case, what is getting raised to the third power? Well, to get to 8, that is 2 to the third power, 2 times 2 times 2 is equal to 8, and that's also I needed x. X to the third gets me, well, x to the third. Minus, what number is getting raised to the third to get me 27? Well, that is. So now in that formula that I'm looking at, this is kind of like my a. It's the first number being raised to the third. It's kind of like my b. Okay, and then I'm going to try to manipulate that formula. So here's the formulas at the bottom again if we needed to refer back to them. So maybe I'll leave that there. So I'm looking at this guy at the bottom. I have a difference. I have subtraction. So I'm going to fill in the first piece. Instead of a, that is 2x minus 3 multiplied by, well, a squared. Got to be careful with that. A squared is actually 2x being squared. Well, that's actually 2 to the second is 4 x squared. So you got to be careful with that. I'm doing some side work, but be careful with that when you're squaring. Plus AB, well, that's really 2x times 3. So that is 6x. And then b squared would be. Notice I'm getting the signs from the formula here. I'm not worried about anything up in this area. I'm looking at the signs from the formula because those will always be the same. Okay, so there's two examples of factoring with the sum and a difference of cubes. Okay. Here's some of difference of squares. Okay, so I said remember to factor completely. We want to factor as much as we possibly can, and that'll come into play over here. But now I'm looking at a difference of squares formula. Well, I know that's a squared minus b squared is equal to a plus b times a minus b. So again, what's being squared here is a, what's being squared here is 7. So that's just a minus 7, or sorry, a plus 7 times a minus 7. It doesn't really matter the order. You know, I could have written a minus 7 first because they're being multiplied. So order of multiplying doesn't really matter. And 2 times 3 is the same as 3 times 2. So not really a big deal there. Okay, now this one's a touch different because I have x to the 4th. But I could write x to the 4th as x squared being squared. So now we could say, well, this is like my a and this is like my b. So that's really x squared plus 9 times x squared minus 9. But when I say factor completely, I want to look at these new quantities and say, all right, can I factor these a little bit more? Well, if I look at this one here, it looks like I have a difference of squares again. X squared, and this would be the same as 3 to the 2nd power to get to 9. So I can factor a little bit more. X squared plus 9 times x plus 3 and x minus 3. So I'm looking to see always, is there more that I can do? Do I have other formulas or other pieces that I could factor more in depthly? So we got to be careful about that. Okay. Now we want to factor the following polynomials. Okay, well, let's see. These are different. These are x to the 4th, x squared. Ugh, that looks not so good. I'm actually going to jump ahead. Solving quartic equations using the quadratic technique. So I'm going to look at this first. We had quadratic techniques, meaning when things were to the 2nd power of this form, ax squared plus bx plus c. When this first number was a 1, we had some easy ways of factoring. So for example, let's say I had x squared plus 7x plus 10. Well, when we did that little x method, this number would be 10, and this would be 7. What multiplies to 10 but adds to 7 is 5 and 2. When this number was a 1, our work was done. Oh, I'm a poet and I didn't know it. But when this number was a 1, your work is done. You just say, okay, x plus 5 and x plus 2. Because if I multiplied this out again, x times x is x squared, x times 2, well, that's 2x, but this is 5x. So combine those, you get 7x. 5 times 2 is 10. So our work was really simplified when this number was a 1. All we had to do is look and see what multiplies to this but adds to this. So that's what we're going to be using here. But the only difference is now it's not x and x. Our powers just went up. Now it's x squared and x squared. Well, that should make sense because x squared times x squared, we add the exponents. That gets me to this x to the 4th. So we're using these quadratic techniques, meaning we're going to factor it just like we factored before. Just the only difference is our exponents are a little different because, well, they started off different. That's really the only difference in what we're doing. So let's go back to these. I'm going to look at making my little x. The top number is negative 50. The bottom is negative 23. So I'm looking for something that multiplies to 50 but adds to 23. Well, I know it's not 1 and 50, and so I think it's 2 and 25. Specifically, I would need to do negative 25 times 2 to get negative 50, and negative 25 plus 2 to get negative 23. And now, like we said, this number is a 1, so my factoring is done. it's x squared minus 25 times x squared plus 2. So there, again, the reason it's x squared is because my powers here were above, they weren't just x squared and x, it was x to the fourth and x squared. Now we want to double check, like we said before, is my factoring done? Well, I'm seeing this. That's a perfect square and a perfect square. So I could go one further and say this is x plus 5 times x minus 5, and then x squared plus 2. So that would be factored completely. I can't really go any further. Okay, so I'm going to suggest pause the video, try number 9 here for a second. And then when you rejoin, I'll kind of have the steps done for that. All right, so here you can see, 9 times negative 7 gets you negative 63. 9 minus 7 is 2. Here's my factored form. Now, this one throws people for a loop sometimes because they see this 9. And they say, oh, perfect square. Yes, I can factor a little bit more. Wrong. Wrong-o. Can't do it because we don't have a difference of 2 squares. We need to have a difference meaning subtraction. This is addition, so I can't really do anything further with this. The second piece, we have subtraction, but 7 is not a nice perfect square. So this is actually as far as you can go. Okay. Last couple examples here. Now we're going to go one last step here. Before we were just factoring. Now we have an equation. We have equal sign here. So an equation, we actually have to solve what values of x make this true. But we're going to start things the exact same way. So what multiplies to negative 14? What adds up to negative 5? Well, I know that is negative 7 and 2. So since this first number is a 1, I'm done. X minus 7 times x plus 2 equals 0. So that's my factored form of this original equation. Okay, and you can always check if I remultiplied this out, it should equal what I started with up here. Now, what are my solutions? Well, what I'm looking for is we're using this zero product property, if you remember that. Since this is multiplication, if this value was equivalent to 0, 0 times anything is 0. So what we're going to do is say, let's set each parentheses. What makes that equal 0? Well, that would be 7. So if I plug that in, what I was saying before, 7 minus 7 is 0. 0 times, I don't even care what this equals. 0 times anything is 0. So that's how I'm getting that solution. And then x plus 2, we want to say what makes that parentheses equal 0. Well, that would be negative 2. So there's my 2 possibilities for that quadratic. That's what we've done in the past. Hopefully that's kind of review or comes back to you a little bit. Let's look at 11. Nothing really changes except maybe I have an extra step. Okay, so I'm still going to factor what multiplies to 36, but adds to negative 13. All right, and then what multiplies to negative 13? Or sorry, adds to negative 13. So I'm thinking this is negative 9 and negative 4, because those multiply to 36, but add to negative 13. And then remember, that's the only difference now is this is x squared minus 9 and x squared minus 4. Okay, now I'm not necessarily done factoring. In this case, I have difference of squares and difference of squares. So what is the value that gets me to 9? Well, 3 squared. So this is x plus 3 and x minus 3. And then I know x plus 2 and x minus 2. That would get me 2 times 2 is equal to 4. So I factored this out completely. Now I'm going to look. What makes this equal 0? Well, x would have to be negative 3. Negative 3 plus 3 is 0. What makes this parentheses 0 is positive 3. And then I can keep going down the line, negative 2 and 2. So this time I actually got 4 different solutions, okay, instead of just 2. All right, so there's another example. Okay, I'm going to pause here again, and I want you guys to try this. This one's tough because your numbers are pretty big. So let's pause and see if you can figure it out. All right, this was a tough one, but hopefully you could figure out negative 25 times negative 9 gets me 5. and also adds to negative 34. And then I can go from there, factor to get to this step, difference of squares, and then solve. That one's a pretty nasty one. Okay, one more example here. Now we have a sum of cubes. Okay, so I might have to review this formula. Let's use this and cover up some other stuff. Sum of cubes, so I'm looking at this guy right here. What's being cubed is x, plus what's being cubed here is 4. So I'm going to use this formula. Instead of a, it's x. Instead of b, it's 4. So now I have x plus 4 multiplied by x squared minus 4x plus 16. That is equal to 0. So I'm going to factor that. And now I need to try and check. Can I factor this more? Or is that all I can do? Well, unfortunately, I feel like that might be all I can do here. I know what multiplies to 16, it's either 4 and 4, but those don't add up to negative 4, or 2 and 8, but those don't add up to 4 either. So I think I'm kind of done with factoring. So we'll have to figure out what can make this first parentheses equal to 0. Well, one of my answers will be negative 4, because negative 4 plus 4 is 0. 0 times all this mess, it's still 0. Okay, but then what do we do here? There's got to be more solutions, right? How am I going to solve and say, okay, what makes x equal 0 in this case? Well, you get to bring back your good old friend, quadratic formula. Quadratic formula, opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Yay! Okay, you get to bring that back. Now let's plug in what we know. Opposite of b, well, that would be 4 plus or minus square root b squared. Well, 4 squared is 16 minus 4 times a, which is 1, times 16, which is, or c, which is 16, excuse me, all over 2a, which would be 2. And you're going to notice something here. Well, what happens? I have 4 plus or minus the square root of, well, 16 minus 64. That's negative 48. What happens in that case? Well, we can't do square roots of negatives. When we do square roots of negatives, we get imaginary numbers. All right, so this would end up being some imaginary solutions. For the sake of the time of the video, because I've already talked forever, I'm going to maybe talk about that at a later time. But we'd have one real solution, and then we'd have 2 imaginary solutions because of that square root of a negative. Okay, we'll go into more detail on that a little bit later. All right. That's it. Happy trails. Good luck.